Hello, good afternoon. I'm finally back. Had a nice break. Read a lot of books, did holiday stuff, and I worked on my Game Jam submission off stream. If this is your first time to the stream, we're working in a programming language called Gleam, and Gleam has a wonderful framework called Tiramisu, which is binding to 3.js. So basically, you can write applications and games that use 3D and run them in the browser and run them in things like I forget what it's called, nw.js, which lets you make desktop apps from JavaScript apps. So anyway, it's pretty sweet. I've been enjoying it a lot, and I learned a lot. If it's not clear, if I didn't say it already, I did not submit my game. I was not happy with it, but I'm glad I participated because I really wanted to break through some of the conceptual barriers that I had had when working in Bevy, and I think that I learned a few things that are really important. One of the things that I think, especially my FP coded brain struggled with for game dev was the distinction between static states which have strong functional properties that you can reason about. So if I'm thinking more of let's say you're playing a game of checkers or chess. You have various pieces, and their positions on the board are static. And when you make a move, it's not necessarily that there's a continuous point between those moves. You can completely represent the game as a sequence of static board states, right? And that sort of thing really appeals to me because it's easy to reason about, and you can do very local reasoning about, I have a given state, what is possible to go to the next state. So that's great, but what it doesn't lend itself to is, even if you have something that's kind of turn-based or at least happens on a regular tick, a regular interval is the minimum interval within which you can make changes. Humans, you get a much better experience, let's say, if you have continuous states. Things like you want your state to not just instantly flip. You want transitions. So you want animations. You want things that happen slowly over time, as well as things that happen quickly, but still they're not happening discretely, if you catch my drift. So this I struggled with. And we'll talk about why. So first I want to... we'll switch over to the main screen so you can see what I'm talking about. This is the game I was trying to emulate. And this is if you've never seen it before, this is the navigation puzzle from a game from the early aughts called Yo-Ho-Ho Puzzle Pirates. And interestingly enough, this game was written in Java and distributed as Java Web Start type app. Now it basically was a desktop app, but you could download it and launch it from Java Web Start, basically. So the premise is that, and this is what we were trying to build an analogous version of. The premise is that you have 8 points on the wheel and 3 rings. So this is a sort of match 3 type game, but with some additional constraints. And as you play, the stars fall in from the outside. Okay, and your goal is to put the stars on each ring in positions such that they match the circled positions. So you can see here, here's a white star. It's supposed to go into this position to solve the puzzle, so to speak. And here's a red star incoming, and well, you'd want it to be in a position where it would line up such that the white and the red star are both in the correct position to fill those circles. And your basic operations are, you can rotate a ring that you have so notice this middle ring is highlighted. That is the one that can be rotated. Now, the mechanics of the falling stars are that if they are in I'm sorry, what they do is they fall from the outside and then they fall to the innermost ring that is unblocked. Okay, so eventually you get to something that looks more like this. Note they're trying to get, they don't have a red star there, so what are you going to do? Well, you try to get, if you need to clear out a spot, you can get 3 stars matched up, either side by side or vertically. 3 or more stars. So like if this yellow star weren't here and they dropped the blue star in there, then those 5 would get removed from the ring. Okay. So, I think you can imagine how this is fairly straightforward to represent as a collection of 3 rings. Each has 8 spots in them, and you can rotate the rings, right? And that rotation could be discrete, like you'd rotate it left 1 spot and it would go counterclockwise, right? Or you rotate it right and it would, move clockwise. Okay, so that's how I represented it. And these spots could be empty or they could be filled with a particular colored piece. So what I did was, we had one data structure represented as a single ring. Our board is 3 of those. And then each spot in the ring is an option of a game piece. Okay. And in this game, I think I determined that there were 5 different colors, and so that's what I went with. And the reason why I have these particular 3 screenshots is I was trying to determine, and this is from a video that's on YouTube that you can watch. I was trying to determine, well, how many spots get allocated per ring, and it looks like there's at most 3, and then there's a total of, like, it looks like 6 or more, up to I think it's like up to 3 per ring. But I think that just from my memory of playing this game years and years ago, I think that you might get 4 on occasion. And the interesting thing about this is we could have that be an aspect of difficulty. So as you get further in the game, you get better. It might increase the difficulty. That's something we can do. Anyway, I was just trying to get the basic mechanics done. But you can see that while this might be fairly straightforward to represent in a very discrete way, it's going to be really unsatisfying if you rotate a ring and it just flips, or if a star just hangs out here and then all of a sudden it's in the outer row. That would be a horrible gameplay experience. So what I struggled with a lot was representing those transitions such that they could be displayed visually. I could handle when those transitions are supposed to end, as well as drive the core game logic of did the stars that were placed here match up with the pattern. And interestingly, like the value for the type for the board itself and the patterns is basically the same type. You have 3 rings And for the patterns, it's just, well, you have a piece that represents the hole that you're supposed to fill, that you're supposed to match. And then there's some pretty straightforward logic of look at the board, compare it to the patterns. Did they complete that pattern? There's a lot of things that I didn't complete. Obviously, I mentioned that before, but this is what we're working with, and I want to work on it a little bit today. I also have a patch or two that I want to do for Tiramisu itself, so maybe we'll get to that. I hope. All right, so let's open up Zed. Now, in order to deal with the mounting complexity of this game, I did a lot of refactoring, and this is probably not going to look at all like what we did on the last stream. So bear with me. I think we had done like loading assets and input bindings and such on the last stream that I did. So there's the main game logic is here in this core module, and the types here is a piece. And I started tracking IDs, and like if this were Bevy, it'd just be like this is the entity, right? And you would attach various components to that entity, or register various components for that entity, and that's not exactly what this is. This is much simpler. But at first I just had, oh, well, it's just this. We have 5 kinds of pieces, and we can represent those visually however we want. But it was like, well, you either have one of these or you have nothing in that spot. But that wasn't sufficient because I wanted to be able to track things like, and this is going to be hard to demonstrate without showing the video. Maybe I'll link to it in the description later. But when you do a match, let's say, what would be a good example? What can you do on one of these boards? It's pretty obvious. Okay, so let's say you rotated this middle ring such that this blue one is up at the top, and then this blue one falls in, and these 3 match, and so you clear them. Okay, so you have, once these 3 match, we want to cue a transition which removes them from the board. Like they, dissipate, they sparkle or whatever. Like you have an effect, you have a transition, and that happens over some period of time. They won't just like disappear. Now logically we could say, hey, they've just disappeared, they're no longer in the board, but we want to be able to represent them leaving the board. So where was I going with that? So the board is somewhat discrete, somewhat continuous, and I'm not sure I've landed on the final design yet, but we're close. So this is just a little counter that we use for generating IDs for pieces that come in. So as the game ticks and it goes, hey, it's time to spawn a new piece, then we'll pick this ID and increment it so that we get unique ones, and then that'll let us track the transitions for each of these things and render them separately. Okay, and then the board state is actually like, did we play? Are we currently playing, or did we fail the game? So if we get into a situation where a piece lands and the spot that it was about to land in is occupied, then you lost the game. And so we would want to reset the board state at that point. Okay, and then there's pieces, and I call them rows, and I think I need to rename this to rings. We may do that. But since like logically in memory they're a collection of 8 pieces, it felt like a row. You could also do this as flat, not as rings. And then there's the patterns, and this is how you determine did they match the pattern, and can we clear those things out. And then the transitions is just set of like this entity. This is sort of, what we would do with an ECS, although not as elegant. We have, an identifier, which is either, hey, you did something to the row. So like you rotated the row is the main thing there. Or it's a piece. It's either falling, or it is being removed from. So, and here's our transitions. So we're either rotating the row, a piece is exiting, a piece is dropping from one row to another. That's significant. So if you said, let's get an example. So like you got this hole right here, right? If you rotated this row such that the yellow or the red piece were over that, you'd hit this spot and you'd want it to fall in. That's a small transition that we should make. So that's something. And then the piece falling is basically the stuff coming from the outside. Okay, and then the position is 0 to 8. The row rotation we can do left or right, which is basically counterclockwise or clockwise. We call the slot its optional piece. Now I went through a bunch of iterations on what this main type should be. At first it was a tuple of 8 spots. Or no, it was a tuple inside a named type with 8 spots in it. And then as I developed some of these algorithms, which like that's fine because you can do pattern matching on the tuple and such, but the logic became really tedious in cases where I wanted to update a single spot, right? So having the named fields in here, and it's just 8 A through H, right? Nothing crazy there, but it became much easier to go, well, I'm going to take the previous row and just update this one spot in it rather than having to pattern match all the time. Okay, so we have the outline of a function to advance the board by 1 tick with this delta time, and then it's like advanced transitions, and then we'll do any like maybe we should add a timer to the board for like when the next piece spawns, and if that timer has expired, then we spawn a new piece and so forth. And then the real fun is in this advanced transitions. So we take the transitions from the board, and the reason this takes a board and not just the transitions, it doesn't just operate on the transitions, is we need to detect when things finish and take particular actions when they finish. So this delta time is passed in with the game loop, right? That's what we're going to operate on. So rotate row, a lot of these are just updating tweens. And you may have seen, I've popped over to it briefly, this Tiramisu animation module is all about things that happen over time. So there are animation clips, which are sort of more like you might create those in Blender or some other 3D authoring tool. I'm only concerned with the simple tweens. So going between 2 values over a duration, and this is how much it is elapsed, and then you pick an easing, and then there's a lerp function, and that lerp function depends on the type, really. So there's some default ones like tween float, which is like between 2 values. We'll use this a lot. And then tween vec3 could be interesting, but I'm not particularly. I think what I'll do is I'll use a float, and then because the positions are very fixed is not the right word, but they're very regular. We'll just turn the float into a particular distance from the origin, sort of thing. Okay, and you can do it with transforms and so forth. And honestly, if you can write a function which is this, you can animate anything. That's the little secret they didn't tell you. So, um, we did that a lot at Fable. Like a big portion of our product was how do we apply tweens to new types. So, updating, like, obviously the floats are straightforward. You know, positions are interesting because we did, a straightforward linear tween is useful, but a more useful one is a Bezier path. So we made Bezier paths, so you could move something, around the screen in whatever direction you wanted, and it wasn't just, straight from this point to this point and then so forth. Colors is super interesting. Obviously you can tween through the RGB space, but it doesn't make that much sense. So I think that what we did was we went through HSL space, which is a bit more intuitive. HSL hue, saturation, lightness. The hue is basically an angle on the color wheel. The saturation is, are you full color or are you muted? And then the lightness is how bright the color is. So that produces a lot more intuitive transitions than the RGB space does. Anyway, I'm getting off track here. That's something that we could add to Tiramisu at some point. We could do tween color. Okay. Okay, so rotating the row. This, I don't think that so it was a float tween, and I think that I probably want that to be the angle. So the main thing here is in all of these is we update the tween, and then we see if it's complete. If it's not, like for this one, if it's not, we just throw it back into the dictionary, and we don't change the pieces. If it is, then we figure out which row it is, and then we finish the discrete transition, right? So we apply the rotation at the end of the transition, and this is the kind of, like, I won't call it a breakthrough, because it's not really that. There were probably other ways to represent this that could be better, but for my brain it was like, probably what we'll do is we'll set a minimum, and I may have mentioned this earlier, we'll set a minimum tick. Like, let's say actions can take no less than 100 milliseconds. Then we can make the rotation be 100 milliseconds, and at the end of that, or maybe we can even make it 50 milliseconds. At the end of that, we can decide whether we want to drop things and give them 50 milliseconds to drop, but make the input buffer be from the player be 100 milliseconds, and that way you couldn't take an action faster than that, and that would give us time to apply all the things in a way that makes sense and doesn't get too confusing. So that was my idea. But you can see here how, like, using the struct update syntax is a lot better than trying to update a tuple. So I started to apply that to basically everything. You have the splat, and then you have the update this field bit. Okay, if a piece is exiting, we have a similar thing. If it isn't complete, just advance the transition. If it is complete, then we want to clear it out of the spot that it's in. So the position here is it's in a particular row at a particular position, and then we clear it out. Now, I could have done this with IDs, but I didn't want to make like a lookup table of this thing is in this position. So I think that for this case, if you have a match or you clear the pattern that is specified in the puzzle, so like you match up, all the spots in every row, in every ring, then we want to make those things, you know, sparkle and exit and so forth. So that's what this is. But in this case, you know, we're going to do this because they're probably going to be synchronized. We're going to do this for every piece in a tight loop. Every piece that's leaving. Okay, so if a piece is dropping, then what did I do? So if it's complete, oh right, so this is not, I think this might be incomplete. Maybe I left it for later. There is a logic for this if it's dropping from one row to another. Oh, right, because I think my thought here was that the piece dropping, this would be like a, you know, n to 0 type transition. When we start this transition, I've already put it in the row below. So I think that that was my thought on this. We may need to revisit that, but this is another one of, you know, is it complete? No, put it back in the transitions. If it is true, in this case, we're just removing it. Like, we don't have to deal with that anymore. Okay, and then this is the falling, which is different from dropping, but this is falling from the, you know, outside of the ring. Okay, so here, you know, again, just update it if it's not complete. If it is complete, place it in the outer ring, and if there's a blocking piece, then we set the board state to failed, and we don't update the ring, and we delete the transition. So we'll probably want to do more here, which is like, we want to reset the board entirely probably for this one. Okay, so you noted up here in rotate row we have a direction, which is either left or right, and the tween. So here's where we handle the rotation. If it's left, rotate left. If it's right, rotate right. This is just functional dispatch. I could probably inline these functions because they're not exported, but for rotate left, this is the one. These two functions I rewrote like 4 times. But you can basically see here that if you rotate left, you shift everything up a slot and you put the first one in the last spot. If you rotate right, you shift everything down a spot and you put the last one in the first spot. Not really confusing. Okay, and so then we build up, did we solve the puzzle? If so, the pattern matches the row. So if the pattern is, and again, I need to call these rings, but if the pattern, basically every slot has to match. So if the pattern is none, then yeah, it matches. It doesn't matter what's there. If it's some and there is a piece in that slot, then they have to be the same kind. So they have to be one of the 5 different kinds of pieces. If it's, you know, if there's any other case, then it doesn't match. So that's a pretty, like, this is why FP is so great. I could do these things. Okay, and the answer for if the board is solved, so like if we matched all of the patterns, the slots here, then it's just every row matches its pattern. Every ring matches its pattern. Okay, and then I did some logic. This is more the discrete stuff, which we'll probably put in the tick. But basically it was like, we want to, from the inside, all of the spots that are open and have a piece in the ring above them, move that piece to the ring below, right? So we do it from the inside out. So we say execute a drop from the middle row to the middle ring to the inner ring, and I'm gonna have to keep renaming these to ring at some point. And then do from the outer ring to the middle, and then update the whole thing. So, you know, this is not that complicated. We're just breaking down the problem functionally such that we evaluate that behavior for every slot in the row. And these are like execute. This is breaking it into two pieces. So deal with the above row and deal with the below row. And I originally had it both at the same time, but it got way too confusing. So because it was like, well, get me A, B, C, D, so forth, and do A above, B below, A below, and you know, this is just more straightforward. Okay, so if we were concerned with the above row, then if the below is occupied, then we don't change it. If there's nothing in the below row, either we're going to drop or there's nothing in the above row. We don't care, right? And for the below row, if there's something in the slot, then you can't occupy it with the thing above, so you make it unchanged. If there is nothing there, then regardless of what the thing is above, either it's empty or it's occupied, you replace that. Straightforward. Okay, and then we get, this logic is used when a piece is falling in, and you've reached the end of its transition, and we want to place it. So here, we're looking at a row and a position which is from 0 to 7, right? And we want to put a piece in it, and that can either succeed or fail. So we look at each one of those, and if the position is unoccupied, basically that's what all this logic is, then we update that position. And this is a place where the piecewise record replacement was super useful versus the pattern matching. It was like this kind of diagonal table looking thing, and it was a mess. And then here we're just clearing out. Now the things that are really missing from here, and I don't know if I put them up here. I don't think I commented them out at all. I have some constants that I was playing with that, like, honestly, I'm just gonna get rid of them. We'll figure it out later. There's some bits that are missing that we still need to do. So we need to have logic that is, we need to discover vertical matches. I think this one is actually really straightforward. And if we discover them, we need to output, hey, these things match, and should be queued to exit. And this one is harder. Not harder, maybe just more tedious. And this is because we can figure out what the local maximum is. Let's see. I think it's 5 is the maximum we need to handle. Because if you have 3 adjacent to one another, it should match and make those pieces exit. If you have, so that means you could have most 2 and 2, and then you put 1 in the middle. So we only really need to be concerned with like matches in the same ring that are up to 5, right? Okay. So so that would be 3 to 5 pieces. And we'll do some funky pattern matching on that. Yep. So that's a bit that I have not coded yet. let's switch gears. I broke apart. You may have seen this when I started the stream. I pared this down a lot, so it was getting really, really hard to manage. Like I wanted to do separate things with the camera and with the lights and all that business, and so I broke it into a separate module and did some, in any other kind of language you'd call it dependency inversion, dependency injection. But I wanted to make it so that I could operate on each of these pieces of the scene separately. So we've got this whole folder full of modules for each scene, each part of the scene. And then we've got the root scene, which is basically just we have a plain ID for it and an identity transformation, and you pass it to children. This is so I didn't have, like, there's some things with, like, you can't have circular module dependencies, which makes sense. But also I wanted to use an ID type rather than string IDs. So string IDs just get sprawling and then you can't have structured information in them. And I really wanted to be able to match, for example, a piece on the board. So like its ID in the scene with whatever data I've got in the game state. And so I think, oh right, and so the ring is like the thing behind, so it's one of these versus the pieces on top, so that's separate. And yeah, and so we have some, I made the lights be, I wasn't sure what kind of lighting I would want, and so I'm like, well, let's just make the lights, incrementally, like just 0, 1, 2, 3, so forth. I probably could have done something with cameras like that as well, but I didn't feel the need to yet. All right, so let's look at background. This is one of the first things we did, as we got that, that star field, and we threw it onto a plane. And you may be wondering, where the hell does this magic number come from? Yeah, it's actually one of the problems we saw previously was that the thing was stretched, and that's because the UV coordinates are square, but the texture itself was not square. So the texture is actually rectangular, and this is just to adjust the size of the plane so it doesn't stretch the background. And then we just, there's probably a better way to do this. Actually, I think that there's like a skybox type thing that we could do that with that. We may do that later. But for now, it's just a plane, and we've got an orthographic projection on our camera anyway, so a plane is fine. Camera real quick. This is stuff we did previously, but I just pulled it out into its own thing. We're scaling the camera based on the aspect ratio of the screen. There's not too much more about that. There's probably a better way to do this. Probably the basic 2D camera rather than the orthographic is a way to do that, but I wanted to have coordinates that weren't pixel dependent. So there you go. Lights I played with a lot. It took me, I'm still not satisfied. But I got a little thing which is fun, which is, okay, so we need some ambient light so that things just show up. There's a directional light which is from behind the player, so the whole scene gets lit in that way, and some minor shadows might get cast. And then there are point lights. and one of them was like, I want sort of a little sheen on things. So this one is kind of like off, away from the main scene, at an angle. And then there's one that rotates, so we get kind of like this, you know, things get highlighted as it moves around. It still doesn't look the way I wanted it to, but I feel like it's closer. So this is like, yeah. So all the lights are at 95, which is above the board, um, but um, but this one is like, hey, at a distance of 5, we're gonna go around and around and around. So we get some shininess on our game board. Hopefully. Okay. Overlay is dumb. It's really just we want a semi-transparent thing to dim the scene, um, when the game is paused. So basically, if we're paused or at the menu, then we throw this over the top. So this is really close to the camera. It completely covers the visible area. And we're going to make it dark, gray, and a 70% opacity. So you will still see the board when it's paused, but it'll be like obviously paused, right? Okay. So for pieces, I haven't done anything yet except for I picked some random colors. We'll figure those out later, whether those work. And then finally the board. Here's the funky part. So this is basically if we're in game or we're paused, we should render the rings. If we aren't, then we render nothing. Pretty straightforward. And then I don't know if I did any of this on stream, but we made some toruses. I don't think I did. And they're concentric. They have the same number of segments on them and the same, width. And then I decided, at first I started with a Fong material because I figured, well, Fong material will still allow you to have specular highlights, but it didn't look right. It really didn't look right. And so I think I switched. No, I started with a Toon material, and it totally didn't look right. I wasn't getting any lighting effect at all. I switched to the Fong, and that didn't help. And I finally switched to the standard material, which, is more expensive on the GPU. The shaders are more complicated. But I gave it a 75% shininess and 0% roughness. And so we can get some specular highlights on it. And the colors I played around with a lot. I'm not even positive that I like this light blue color, but it does show off the highlights pretty well. And then I just put them all at the origin, 100 units away from the camera, basically. And then here you can see me using these IDs with integers in them. So we have 0, 1, 2, so forth. Yeah. So I should, what's the error here? Oh, did I accidentally type something? Yeah, I did. We should get this running. Gleam run, dev start. I haven't changed anything in here except some comments, so it should still display. And we're going to do localhost 1234. So here's what we've got. You can see those light blue rings. We've got the background, which is the star field, and I've kind of muted it a bit. But the big thing is you can see the light going around, and it's causing these highlights to rotate, which is cool. Like, it's not so important on the rings, but when we get to actually having board pieces on here, and this is still I'll still want to adjust the radii of these things and so forth. But we got some shiny. So I think I've explained enough. Oh yeah, there's some stuff in UI I haven't really done anything with. Game state is just this, typical top level game state. There's really not anything new in here except that I just refactored it all into separate modules. Okay. Wow, that took 45 minutes to talk through. I hope that was I hope that was interesting to you, useful. Um, yeah. So I think that what we can do for a little bit today, I want to give some time to do tiramisu patches. But I'm gonna let this run. We can look at the sparkles, the shininess from time to time. What's interesting though is I'm changing the well, get below a certain aspect ratio and it gets borked. So I've got a problem there. But for the most part, it scales appropriately for the screen size. That's good. Okay, we will get back to that. I think that we should do this. Let's do. What do we want this to look like? So I think it's we'll break the problem down similar to what we did for the drops. So I kind of want we want to break this down. So I think that we'll operate on the whole board. But we'll break this down by column. So say by column, if all three pieces have the same type, we want to our goal here is to queue up the P's exit transition. Okay. So I don't know, we'll make this like check vertical matches. And I think that this will just return the board. So and it's going to complain that this hasn't is not being used. So I think that probably what we could do is, where's our tick function? Yeah, so I think that we can do like, let's turn this into a pipeline. We'll do advanced transitions. And then we're going to check vertical matches. We rename it to, well, we'll put it in here, right? And then we'll make a function which does check horizontal matches. And then it's apply drops. So let's go to the end of the file here. Okay, and I'm just going to do the no op on that, and we'll do the no op here, and then we'll figure this out. I just want to make sure that that doesn't. Okay. Right, so this will be like anything that is finished dropping will apply it. We're going to have to do something in here which is don't directly apply them, but we'll make a, I'll comment this out, but we'll make a queue drops because some of them aren't going to happen yet, right? So whereas here we're just, making sure that they happen, we want a separate one which adds the transition without applying it. Okay. So vertical matches. I want to rename this now before I get vertical matches. And we'll rename this one as well. Okay, for this, I want to we're going to break it down into a single one. So we're going to have lower is a slot, middle is a slot, upper is a slot. And what we want to do here is return so we want to return a dictionary of entity to transition. So we can basically loop through each of the spots and the spots in the ring, and then merge the dictionary transitions together. That sounds good. We're going to need a position though, and that's going to be from 0 to 7 so that we can create that piece exit. Is that right? Here, let's go to definition there. Yeah, so it has a row name and an integer. Okay. So since this is vertical, they'll all be in the same position in their rows. Okay, so I mean, do we do pattern matching? Yeah, let's do pattern matching. So I'm going to say lower, middle, upper. And if this is sum, and we have a piece, and we have what is the definition of this type? So we have a kind and an ID. Okay. And we're going to duplicate that. And we're going to say this is middle kind, middle ID. And upper kind and upper ID. Okay. And then we need a guard on this. This is getting a little complicated, but we need a guard on this. If LK is MK, and LK is upperkind. So if they're all equal, so we don't have 3 col in Gleam. You can tell I've been doing JavaScript at work. Okay, so if it's anything else than this, we want to return an empty dictionary. So these are not any new transitions to be made. But if we match vertically, then what we want to do is return dict from list. And this has to be an entity to a transition. Okay. So okay, so we want the entity to be a piece entity for this ID, right? And we want it to be a piece exiting, and the position is row name is lower, and the ID is LID. And then the tween, and honestly we can reuse the tween. Animation, and there's probably some problem in this file where it's not. We're just going to go from 0 to 1. I don't know what that's going to mean yet, and we'll tweak that later. Okay, and then we repeat that for middle. And upper. Okay, and what's going on here? Oh, I need an arrow. Okay, so now we're getting the problems. Okay, so this got 2, expected 4 arguments got 2. Okay, so it takes, so we want a duration. So let's make. I'm gonna put these constants. Match. Let's say piece exit duration, and we'll make this 100 milliseconds for now. Okay. And then the easing, this is where I actually got to we should look at yeah, I know. I was looking at this the easing cheat sheet, and I kind of wanted some of these, like you know, in out back was one that I wanted, but that's not part of Tiramisu yet. So I started, this is the patch that we'll get to in a few minutes, I hope. But you know, elastic and bounce are also really good. I think I wanted ease in back, so like it grows a little bit and then it shrinks was the idea. In which case it'll be 1 to 0, right? what's row name? Inner, middle, outer. Okay, inner, middle, outer. And let's rename these. Inner, middle, outer. I know, I'm not great at variable naming. I'm going to fix that in a second. Here, one more rename. I know I'm being a little bit tedious. I'm going to call this iKind. That way we don't get mkind confused with OK and the kind. There. Okay, so let's do Tiramisu doesn't have all these, like I mentioned. The easing types it has. Let's pick one of these. Like probably cubic. Let's see, ease out cubic. Actually, ease in cubic. I want it a little faster. Yeah, I don't even think she has exponential. I mean, I understand, like, it can be kind of tedious to code all of those. Let's pick cubic for now, and then we'll switch it up later with my patch. Because I want something like the back one. So, okay. So now, we can think about how to break this problem down. And the way I'm thinking about it is make a list. We're going to do rows, inner, middle, outer, board.pieces. And then we're going to go yeah, so we'll do vertical match 0 inner.a middle.a outer.a. Okay, and we're just going to duplicate that. I mean, we made too many. Yeah, I made one too many. Okay. And that's going to stay this, and these are all going to be B. You can see how, like, even though this is a little bit tedious, how this is better than trying to pattern match all those freaking rows as tuples. I guess I could do .0, .1, .2, and so forth, but that's fine. Okay, and then we're gonna pass that to list fold. And we're gonna fold over board transitions and use dict merge. And this is gonna be transitions. And then we'll do right, so that's not so bad. And I think breaking this problem down into the essence of it is a good way to go. The horizontal matches are going to be trickier again. We'll want to do... All right, what did I do wrong here? Oh, right, so this is a row name and integer. This is not... So this is wrong. This needs to be position. It's like it was warning me, hey, you didn't use this variable. Yeah, there's a good reason I didn't. Okay, because I wasn't thinking. Okay, it should have been right there. So now there's a question in my mind about whether okay. Here's a potential problem as well, which is making me think about we want this to only detect new matches, right? So I think what we want here is we want a blank dictionary because we don't want to, if something is already queued to exit, like we're just on a new tick and we say, are there any new matches, right? If it's already got a transition queued, we don't want to reset that transition. So I think what we want here is we want to merge the board transitions on the right. So like see if we go to the definition of this, if there are entries with the same keys in both dictionaries, the entry from the second one takes precedence, which is what we want, right? So because if there's an existing transition on this thing and we detect a match, we probably previously queued it, right? Now another thing we could do is say something more complicated, like, you know, don't generate them if they already exist. That sort of thing. But this is probably sufficient for our first pass. If we need to optimize it later, we can optimize it later. And actually, let's just inline this here. And I'm going to put a note here that says ensures existing transitions aren't overwritten. or reset. And we'll do the same in the horizontal ones, right? Okay. So let's think about horizontal ones. We need to evaluate each ring. And I think we can pattern match on a ring at a time. So the interesting thing about this is what we'll do is something similar to this, right? Okay, so I think that we want this to be like okay, so we'll do Q horizontal matches row, and we'll pass it like inner, and we'll do, so I'm trying to break this problem down. I'm doing it top down this time instead of bottom up. And then we'll do this list fold again. Dictionary not new, dictionary not merge, and then we'll do a final merge with board.transitions. And then we'll say board, right, transitions. Okay, so now we need to define that function, generate the function. Okay, and we'll just call this row, not that. So we're going to break this down again. And we're going to do we'll call it 5, right? I'm not thinking right. Row name, row, okay? And then we'll do horizontal 4. Yeah, I'm thinking about what is possible. So you can only have one 5 match because there's only 8 slots. Technically, you could have 4. You could have more than one 4 match. But at any point that won't happen because you're reconnected. All right, folks. Sorry, I lost you there. Okay, we're no longer dropping frames, but chat has not reconnected yet. My apologies. I am recording this, so if the stream recorded by YouTube gets messed up, I'll re-upload. Not sure why that's happening, but here we are. Okay, so I kind of want to do something like what we did above. Okay, so I think the thing is, I could conceive of, it's possible to have as many as 3 matches. But how could that happen? Okay, so let's say you had 2 slots. There were 2 and 2. And then you had the matching pieces offset, and you rotate, and then they fall in, and you match 2, 3 segments at once. That's a possibility. So I think that we need to handle that. So what we'll do is I want to discover, pattern matching the order of the clauses matters. Here, and I want to turn this. This doesn't need to be piped. Okay. So let's go ahead and generate these functions. I love that it gets the it gets the types right when you generate them. Okay, so I want to start with 5 because I think that that's going to be more straightforward. And I think what I want to do so, like, because there can only be 1 5 match at a time and probably 1 4 match, can we conceive of a way, like, actually the same thing could happen with 4 as happens with 3. So there could be 2 4 matches, and there could be 2 3 matches, but there can be only 1 5 match. Okay, so this was the simplest one to do first. Okay, so we're going to do case row. And what I want to do is enumerate all of the possible. So we're gonna have an empty case here, and this is just going to return an empty dictionary, right? This is the pattern we're doing. Okay, but we're going to have a case where what we want is to pattern match on it starting in each of the spots. So we're going to need 8 of those. 1, 2, 3, 4, 5, 6, 7, 8. And I think that I want this to be in, this is not going to be a, I think we're going to return none here is what I want to do. So we're going to say matches. We'll call this matches. And we're going to do, so we'll do first 5 slots. So we don't care about F, G, and H. And then we're going to move it right 1. So we ignore A, and we do B, C, D, E, F. We ignore G and H. And then we're going to ignore A and B. We do C, D, E, F, G, and H is ignored. I should have put to do on each of these. Okay, then we'll ignore A, B, and C. Now, what we can do eventually is just ignore the rest of the row. So that's the last 5. And then we have the wraparounds. So there's always going to be 3 ignored. And you can see how this might get a little bit messy for the 3 matches because there's more possibilities, but that's okay. What we'll do is we'll do it like in 2 passes. We'll do the ones going clockwise, the ones going counterclockwise, and that way if there's 3 matches, we get both of them, rather than having in this case where like there's only 1, right? I said this would be easier, but it's not necessarily. So I think that so what I want to do is now similar to what we did up here, where we're like checking all the IDs. We want to do sum piece kind equals K1, and I'm gonna actually, let's put it here. So I'm going to copy this into, this is going to be a hellacious pattern match, just fair warning. But what I want is the right-hand side to be all the same. And maybe what we can do then is, if we make that possible, then we'll turn this into not a splat, but an alternation on the pattern. So I think what we can do here is like, let's actually remove the, what's the error there? Yeah, it's just complaining about that. So interestingly though, I think, yeah, so this requires, yeah, let's get rid of the ones that are ignored. Maybe I'll clean it up a little bit. I was just doing it initially to kind of feel out what the pattern would be. But what I want to get to is all the matches kind of coming out the same. Just for my sanity. But here, actually, on the ones that wrap around, I think I actually want to put a last. So, and hopefully you'll understand why in a minute. We'll get rid of BCD, and this will actually be for E, right? E is first. Yeah, I shouldn't have done it that way. Okay, so we're gonna do F, G, H, A, B, and let's put this here. Okay, so we're gonna do G, H, A, B, C. And then finally H, A, B, C, D, and the rest are ignored. Okay. So let me copy this. What I'm trying to get to is so I'm going to copy this, and I'm going to go like so, and just do ID2, kind2, paste again, ID3, kind3, paste again, ID4, kind4, probably a better way to do this, and kind5, ID5. Now, because of the way this transition is defined, I need to know what each one is, so I think I'm going to... Oh, this needs the dot dots. That's what's wrong there. So I'm going to define this again. Oh, shoot. Here, let's remove the split. Okay, so... Why are those lining up incorrectly? Okay. Okay. So we're going to do let's see if I add a return if it still works. Yep. Okay. Craziness editing all this. So what I want to do is come up with, here, let's back that out because I have not put the basically if these are all the same is what we want in that guard. Okay. Multi-editing is going to break my brain, but that's fine. So what we want here is sorry, it wants to reinstall Dash. Okay, we're looking at, I want to do something where we determine what the, the position in the row for the thing is, based on a module over 8. The problem is this returns a result. Okay, so do we just use that? Is that just a built-in? Yeah, I think we do. Okay. So, we're going to return some. There's a question in my mind of whether I want to do, yeah, let's do dict from list. Okay, and we'll say row entity, no, not row entity, piece entity. Yeah. The piece entity is going to be ID1. And then we'll duplicate these and, and so forth. And then it's going to be piece exit. Position is row name, right? And then base position. And here's where I think I should make a function that just gives us the default tween. So maybe what we do is let's make actually a function that generates this whole struct. And this is going to be row name position is in. And this is going to return a transition. And let's just do this, right? And this is the, and we can just put it in one place and we'll reuse it. So this is row name and position. And yeah, let's convert this to piece exit, and then we'll go back to our other function and do the same for everything. Except my editing is going to be messed up. It's all right. I can copy paste instead of doing multi-row edit. It's fine. Row name is inner and position. Okay, so there. Excuse me. Okay, I'm no longer dropping frames. That's good. Chat, I don't know if it connected or not, but there. So we refactor that out, and we can, construct this transition consistently across all the places. And so now what I want to do is okay. This is going to be piece exit transition. Row name and base position. Okay, and then we're going to do the other 5. So get 5 of them, ID 2. And this is a +1 mod 8. I don't technically need to do it on this one because I know they're not going to wrap. But what I want to do is, I'm sorry, and this is ID 4 and ID 5. What I want to do is just reuse this and update that base position. And then they'll wrap around automatically and yada yada. Bob's your uncle. Okay. So what is it complaining about here? Yeah, we're not returning the right thing. So we will do this. So base position 1, 2, 3. There's probably a way to do this more elegantly, but hey, games are always full of messy code. This is a little bit of mess I can handle. Okay, and then the last clause should be none. Okay, and then we're going to do option unwrap. You don't really need. Yeah, let's do lazy unwrap. Dick new. Okay, so we don't need this binding. We can just say case row and pipe it into there. Okay, so now that is really long code, but hopefully what you can see is that we're matching all the places. In the row where there could be 5 that match, right? Now, potentially what we could do is break this into where we just get the pieces in each slot. And then we do a case of if all their kinds are equal. And so like we could break that into a function. That might make these things a little cleaner. So the function is just either all the things I was passed match or not. Okay, so we could do, let's make a function horizontal match 5. And let's make it take the row name and the base position. And I think I want to make a type for this. That is getting a pain to type. And then let's find all these. So this will be transitions. Okay. So what we can do, we can do similar to this. The interesting thing is that we can just like iterate over all the spots. And then slap them all together because there's only going to be one. This is actually probably a good pattern to follow because if we're trying to do the 3 match, then we'll make sure that we get all of the spots. Yeah. I want to be really exhaustive here. I could see us even generalizing to an arbitrary number of slots. And so you would do 1 pass. Yeah, I don't know that that would be any better. Let's do a little copy pasta. So case, we're going to do case S1, S2, S3, S4, S5. And then we're just going to get rid of this. Right? And let's put the same guard on there. And now we're passed in the base position, so we can just do copy this. And if it's anything else, we return an empty dictionary. Okay, now it's just complaining this isn't called. Yeah. Okay, so oh, that feels good. So now what we can do is simplify this a lot. Oops. We can go zero. All right, it's 3:15. We'll get some. We'll look at my patch in a minute. So I'm just going to do the business of rotating right. Okay, now we start wrapping. It's gonna be easier to do this than do all those deletions. Unfortunately, this is the sort of thing you have to do when you're doing game dev. You sometimes have to do things that aren't pretty. But I feel like for this particular problem, these are useful useful abstractions. And again, like coming down to the whole what things are cumbersome and what things are easier. Here, let's convert to a function call for that since, okay. Interesting, the other thing that we could do here is just use this as the first, as the accumulator, but it doesn't really matter. Okay, so I think we have sort of a framework and a pattern. And then we can go and do this for 4 and 3 as well. Another way I thought of that we could do it is have a function that says pick me this position from a row from 0 to 7. And then we could say have another function that says pick these positions from a row as a list. That's straightforward to write if we have the first one. And then we could go from like loop over 0 to 7 and pick me 3 positions, so it's like a list take, right? Pick me 4 positions, pick me 5 positions, and of course, modulo 8. So like there's little things I'm thinking of where we could generalize this and then just have this call be like horizontal matches and like the row name and the row and how many. Yeah, I think that's a good thing for next time. And I may work on this in the week when I need a little bit of break. But so that would change this sort of structure to a given these things, make sure that they all have the same kind as the first one. Not sure how I would express that yet. And then if they do, then map over them, taking their ID and then generating the kind based on the index into the list. Like that sort of thing is I'm sorry, not generate the kind, generate the transition based on the index into the list. That's the sort of thing I'm thinking of. Yeah. So maybe that's what we'll do next time. Let's look at the tiramisu. So I mentioned I was adding easings. We had easings on of course we did them differently. The main reason being we wanted to have an easings editor, and I don't think that that's necessary for tiramisu. Now what we could do is something I'm considering. Um, this is like you want to just pick a named easing. But I think that what we should do is also have an ease custom such that you can define your own function for the easing. You could do disjoint transitions, that sort of thing. But what we did at Fable was our easings, we had some stock ones that you could name, right? Like you say, hey, I want the exponential, or I want the bounce, or whatever. And that corresponded to basically a set of Bezier curves. So I say set, it was like a sequence, and you had each of the points and the control points. And what that let us do was have an editor where you could like tweak the control points or add new points or delete points from the easing. The But that meant that, like, floating point error crept in. You might not recognize something that is one of the stock easings as that easing. It just looked like a set of Bezier curves. So that was potentially a problem, or that was a thing. But I think for this, like, it's the hard part about that. It was good that we had the editor, but it meant that we traded off some efficiency in terms of computing the default easings. Because it's like if you said, oh, well, we'll have these default ones, but then you can make a custom one, there would have to be a way to convert from a default one into the corresponding custom ones. But what Tiramisu does is it just says, because there's things I've added here, we're just going to do the computation for that easing. And I think that that's the most efficient way. It's like, given anything on this, this one-dimensional space, how do you map into this other one-dimensional space through the easing? So it's like conversion from T to T. But you're doing things like, linear is just like there's no transformation on it. Quad is you are multiplying it, so it starts slower and then it it speeds up as it gets closer. So this is the sort of thing that, like, this is way more efficient. And I think I was doing this over the holiday. I basically copied this stuff from that easings.net. So some of them are more obvious to do. There's some issues here with using the power function on float, in that it can return a result. Obviously, if you have something that you do fractional power of -1, that's not defined as a real number. That's an imaginary number. So if we luckily here we can know that since this is 2 to a power, that it's never going to return an error. But yeah, we have to account for that. So I added all of these. I think I finished all of them. The bounce one is crazy go nuts. Look at this business. At least you can define the in and the in out as a function of the out. So what are you gonna do? All right, so there's some magic numbers in here I'm not real happy with, but so I had added quartic tests for quartic and quintic, and we just need to add tests for all the other new ones. So exponential and circular and back and elastic and bounce. Okay, so some of these they're just checking that it doesn't error. We could, there's a float. What was I doing? There's a float loosely equals where you can specify a tolerance. We could do something like, you know, assert loosely equals on these things. So we did quintic and quartic, and let's do ease exponential in test and out test and in out test. I think what I did on a bunch of these was just like pick some numbers and like do the computation myself. Just by looking at the easings.net. Yeah, so if we're doing exponential, I'm not sure why they'd multiply that by 10 and then subtract 10. Maybe that's just more for more precision. But we could say something like the easy ones are like this stuff, you know, this sort of thing. You come to the, you're at the extrema of the easing, and you should be roughly at those. It's the stuff in the middle that's more interesting. So if we say so at half we should be at 2 to the negative 5. So 1 over 2 to the 5. So 1/32. So we can copy that. That's a good thing to check. And we could say like if it's let's do another one that's just a sampling. Let's do at a quarter of the way, so that would be 2.5. Let's see, 10 times a quarter. So 2.5 minus 10 would be negative 7.5. That's maybe not the best. Let's try to get a whole number. Let's do a tenth. So that's 2 to the negative 9, which would be 1 over 2 to the 9. So 2 to the 9, 5/12. 1 over 2 to the 9. 1 over 5/12 is that. So these are the sorts of things you can do just using the intuition of it. Okay, so maybe we could do like 0.9. Yeah. Let's pick like 0.9. Okay, so this is going to be 9 minus 10, 2 to the negative 1. So we should be at a half, right? Again, just like checking my assumptions on these functions. So let's run the test. Okay, so that one passed. We added a new test. It's fine. So now we can go. The out should be an inversion of this. Like these are kind of tedious to write at first, but then you like find ways to be. So this would be 1.0 minus this. Except this is a tedious thing about Gleam. I actually wish that they had. I understand why they don't, but okay. So I actually have a problem here, and that's I didn't change the easing. Oops. Okay. I wonder if I have a bug there. So it's saying 0 is not 0, but 1. This might actually be a bug. And 2 to the 0 is 1. So I think that, what does ease out exponential look like? At 0, it's still 0, right? So I think that I need to add a clause here, which is 0, right? Okay, and here's the thing where my assumption about how this works is wrong. Actually, it's that, you know, at 0.1, it's the value for 0.9 here. It's not 1 minus that thing. This is going to be 0.9 here is going to be 1 minus this, right? What's 1 minus 0.03125? This is going to be like 511 512ths. which is this. Yeah, I'd rather express it as constant. Okay. So I think I actually do have a bug here. Let's look at this. We need that 1 minus. That's what the problem is. I don't need this clause. I need the 1 minus. That's what I need. Okay, now they pass. Yeah, so this is good. Found a bug. Always good to do that. So now the last thing, and then I'm going to cut the stream because I think that this is not really interesting content. And then we'll come back to the game next week. Hopefully I'll be able to do this, the rest of these tests off stream. Okay, so the in-out is interesting in that we're going to have, you're going to reach the middle at the middle with a lot of these in-out transitions. When you're at 50%, you're at 50%. If you're 50% on T, you're at 50% on the transformed. So, so they meet in the middle, and you kind of have half the curve, or like half the curve is the ease in, half the curve is the ease out, and then and you join them at the middle. So we're gonna copy some of this, and we'll just modify, and then I'll call it. Okay, so what we're gonna do here is make this ease in out. So what we could say is things like we expect it to traverse the same, or a scaled version of the space is maybe a way to think about it. Expect it to traverse half the space in half the time. So if we look at the inside and we say this is what it is at 0.1, I expect that to be it reached that at 0.5. That may be a mistaken assumption. Let's test it out. Yeah, so there's a problem here. Let's see if that's 0.1. Interesting. I wonder if that works because it's not, because the scaling. So then on the out, I think if this is the case, then I expect this as well to be the same. Let's make sure we don't have a bug. Oh, note that they scaled the power up here. Okay, let's look at ezines.net and make sure this is correct. Okay, so the in-out exponential. Okay, so if x is 0, return 0. If x is 1, is return 1. If it's less than 0 to 5, then you do 2 to the power of 20 times x minus 10 over 2. It looks like they're distributing this divided by 2. I was like, why not just subtract one more? Why do I know? And then of course you do the 1 minus for the other direction. But it's multiplied by 2. I was like, why not do 1 minus r divided by 2? But this is the way it's expressed. I was trying to copy it as exactly as I could. 20 times x minus 10. Okay. Negative 20 times x plus 10. There's a little bit of, did you like distribute the inversion here where you shouldn't have? Did you write that specifically for JavaScript's math system? I don't know. This is one bit where I'm like, can you just give me the mathematical function? And not some implementation in a very JavaScripty style. All right, I think this is a good place to stop. See you next week. Hopefully I won't have problems with the stream next week. And we'll do some more of patches to Tiramisu and working on the Game Jam thing that I never finished. So should be fun. Hope to see you then.